Hello everyone, I'm Myisha with Chowdhury and it is my pleasure to present the article Stability Preserving Automatic Tuning of PID Control with Reinforcement Learning. The authors of this article are from Texas State University. PID controller is one of the most dominant type of controller available in process industries. However, there are some roadblocks for PID application. First, the control performance of PID strictly relies on the setting of its parameters. Despite the fact that some guidelines are available for tuning PID controller even for complex systems, the resultant PID parameters may not be the optimal values. Second, the parameters of traditional PID controller generally remain fixed after tuning. When there is change in the system complex, it lacks in adaptivity. Application of reinforcement learning for the tuning of PID parameters have been effective in mitigating the above issues. However, preserving stability during reinforcement learning exploration has been an issue. The main contribution of this work was to develop a stability preserving automatic PID tuning approach based on reinforcement learning, particularly the DPG algorithm, which is a deterministic policy gradient algorithm. Our strategy uses a baseline controller to replace unstable PID control in order to maintain the stability of the system. Adaptivity of the reinforcement learning PID tuning to change in the process variable process parameter is also explored. So reinforcement learning is, what is reinforcement learning? Reinforcement learning is a type of machine learning technique that enables an agent to learn in an interactive environment by trial and error using feedback from its own action and experience. The objective of an agent is to find the best policy such that the long-term cumulative reward is optimized by interacting with the environment. There are different model-free reinforcement learning algorithms available. Among them, the deterministic policy gradient or DPG method received wide attention due to its simple sample efficiency by considering the deterministic rather than stochastic policies. As a result, the usage of off-policy actor-critic-based DPG algorithm has shown attractive prospects for addressing the PID tuning problem. There are 4 networks involved in the DPG framework. One is actor network for selecting action based on the current state. Second one is critic network for evaluating the current Q value function. Actor target network for selecting the best action for maximizing the next step Q value, and critic network for evaluating the optimal Q value for the next step. This figure shows the schematic of a stability preserving reinforcement learning PID based tuning. The proposed scheme is a multi-scale in time for reinforcement learning and closed loop operation. The closed loop system here with PID control is viewed as the environment. The output of the environment are the trajectories of process variables such as the manipulative variable, control variable, and set points throughout an episodic closed loop simulation. Each closed loop simulation gives one sample of state and action transition of the environment. The parameter of the 4 networks in the DPG algorithm are updated once as soon as one episodic closed loop operation is complete. At the end of each closed loop operation episode, the set point, manipulative variable, and and the control variable trajectories will be consumed to extract the environment state, action, and reward. These informations are then saved in a replay buffer, and a batch of sample of past transition data are then randomly sampled to be used as the data set for updating the network parameters in the agent. To ensure stability, a supervisor mechanism is used at the top of the closed loop system to monitor the process variable at each operation step. The supervisor accumulates the running reward or running tracking error at each operation step and compared with the benchmark reward. The proposed method utilizes a conservative but stable PID controller as a baseline. The baseline controller can be selected on prior knowledge of the system and classical tuning guideline. The figure 3 shows the structure of an actor network and critic network and their target used by the agent in this work. In the actor network, layer of normalization is used before each network layer to maintain the stability. Decaying noise is added to the output of the output to encourage exploration at the beginning of reinforcement learning technique. Here, a Gaussian noise was used. Right in the right, the critic network that consumes state and action and returns the Q value for update with policy gradient. So we have applied our stability preserving reinforcement learning methods in 2 cases, and we have used a second order plus dead time model for simulation purpose. For the first case, PID tuning is used, but only for 2 free parameters. The top left plot shows the learning curve of the reinforcement learning during training, where the red curve shows the moving average reward value over episodes, and the blue noise curve shows the raw reward values. After initial exploration, the reinforcement learning agent was able to converge to the optimum. The right plot shows the stable and unstable regions in the PID tuning, where the white space shows the stable region and the red space shows the unstable region. The green dots are the explored parameters by the reinforcement learning agent during the training, whereas the purple dot shows the distribution of the actually implemented parameter. We can see that all implemented parameters are located within the stable region, despite the explored parameters are in the unstable region. Even for the worst case episode, due to the presence of early correlation from our stability preserving algorithm, the control variable and the manipulative variable can still converge to the optimum value. For the second case, we have used 3 tunable PID parameters. However, for better clarify or to make a comparison with the traditional reinforcement learning control techniques, we have made a comparison. We have used a manipulative variable with range from -40. We can see that though both the stability preserving and the traditional reinforcement learning converges at the same time. However, for the worst case scenario, the traditional reinforcement learning method can go as low as -40 initially. The top plot shows the scatter of the implemented PID parameter value under these 2 methods. The light blue surface is the separation between stable and unstable region in the parameter space, where the volume behind the surface is the unstable region. As shown in this plot, all red points, that is the implemented PID parameters with our method, are strictly located in the stable region, whereas some green points are behind the surface in the unstable region. The bottom left plot compares the control variable and manipulative variable of respectively for the worst case episode of these 2 methods during the reinforcement learning technique. It is clear that even for the worst case episode, the control variable still converges to a steady state. Finally, we tested the adaptivity of our method to system changes. It can be seen that after the system change in this point, the control performance starts to deteriorate. Since the previous well-tuned PID parameter may not perform well under the new operating condition, the reinforcement learning starts to gain experience from the degraded reward, and after a number of interaction, eventually the reinforcement learning agent is able to generate quite good PID parameters to adapt to the new operating condition and recover the control performance. Finally, we can conclude that a novel multi-scale episodic PID tuning framework is based on the DPG algorithm is proposed, and the simulation result shows that the proposed method can find both optimal parameter and maintain stability during the reinforcement learning PID tuning. And the proposed method is able to adapt to system changes without requiring any knowledge about the underlying operation condition.